All right, so we're going to go ahead and start off looking at this example right here, and then I'll kind of describe what we're doing from there. So this example is old news. We've actually done something like this before. It says find the equation of the tangent line for this curve at x equals 0. So if you guys remember, to find the equation of the tangent line, first we have to know the x and the y coordinate at that point. So we have to think about, I'm going to draw a little sketch on my unit circle. Sine of 0, I'm plugging 0 in for x, is going to be right there. So that's a degree measure of 0. The point right here would be the point 1, 0. So sine of 0 is 0, because that's the y coordinate. So there's that. To find the tangent line, you take the derivative of the function, and then you figure out what the slope would be at this point specifically. So the derivative, f prime of x, the derivative of sine is cos. So the derivative of that is cos, and then we want to see what the derivative is evaluated at 0, and of course cos of 0 is 1. So that means that the point, the x and the y coordinates are 0 and 0, and that it means our instantaneous rate of change at that point is 1. So we're going to say the equation of the tangent line is y minus 0 equals 1 times x minus 0. Or we could just say y equals x. All right, now they're saying to use this to approximate sine of 0.2. So that means that sine of 0.2 is approximately, well, if I plug in 0.2 for x and I get 0.2 as an answer, so approximately 0.2. Is this an overestimate or an underestimate? So you have to think about what is happening to the graph at that point. So a sine graph looks like this, and at the point 0, 0, the sine graph, that's part of the sine graph that is concave down. So this would be an overestimate because sine x is concave down at 0, 0. Right, so that point, that decimal 0.2 is an approximation for sine 0.2, but it's a little bit high. That number's a little bit too big. All right, the equation of the tangent line is called a first degree Taylor polynomial. And that's what this video is going to be about, Taylor polynomials and then MacLaurin polynomials, which we're going to look at in just a second. All right, so it says Taylor polynomials of higher degree. So the higher your degree is, the more points you're kind of taking into account, the more accurate your guess is going to be, or your approximation is going to be for non-polynomial functions. So we're using a polynomial to predict what this cyclic function would tell us, and we're going to be able to use it for exponential and logarithmic and things like that. So if you look at this formula, it looks kind of crazy, but it just says take the function evaluated at c and add to it the derivative evaluated at that same c multiplied by x minus whatever c is. And if you look at this, the derivative evaluated at c, this is the m, and then this is the actual letter x minus whatever you get as that x term. So we're looking up here and we can see that this was just taken from this part and stuck right down here. And then they're going further than that. They're saying now take that and multiply it by the second derivative divided by 2 factorial, and then whatever x minus c is squared. And then keep going. So whatever degree you're looking at, do it that many times. So if they say to use a 17th degree Taylor polynomial to approximate the number, then you would go all the way out to the 17th derivative. It would be divided by 17 factorial. It would be multiplied by x minus c to the 17th power, and you would add all of them up all the way up to that to be able to get your answer. And so that that's all we're saying here. This f of c part is kind of like if I did have a number here that was something other than 0, then it's saying I'm adding that number over to get the y by itself. So that's what this number starts off with here. So it's just saying get the y alone and then do all the other stuff, but we can do it for multiple derivatives, which is kind of interesting. So this formula right here is called the nth degree Taylor polynomial for f centered at c. And c is that whatever that x value is that they gave you in the beginning that they wanted you to do it based off of. All right? Okay, now we have MacLaurin polynomials, which are a very specific situation of Taylor polynomials, and that's when c is 0. So the one that we just did is actually a MacLaurin polynomial. And so here it simplifies things a little bit because you don't have x minus c. Since the c is 0, that would be x minus 0, and that means that you just have x and x squared and x to the third or whatever for however many of those different steps that you have. All right, so let's go ahead and look at example 2 so that we can see exactly how this would work. So it says find MacLaurin polynomials P1, P3, P5, P7 for sine x. So we're going to go ahead, and if we're going all the way to the 7th, we're going to need the 7th derivative. So I'm going to say my first derivative of sine is cos. My second derivative is the derivative of cos is negative sine. The derivative of negative sine is negative cos. The derivative of negative cos is sine. Now it's going to start being repetitive, but I'm going to go ahead and write them anyway. So the derivative of sine is cos. I'm going to leave myself a little bit of space. You'll see why in a second. So my sixth derivative is negative sine, and then my 7th derivative is negative cos. Okay? Now, to be able to use the formula, not only do we have to know what the derivative is, we have to know what it is evaluated at 0. So, if I'm going to go ahead and think of my unit circle so I can do this quickly. So if all these are being evaluated at 0, so that's the 0.10. All right. So cos, if I evaluate this at 0, then cos is going to be 1. So the first derivative evaluated at 0 is 1. The second derivative evaluated at 0 is 0, because it's the y-coordinate. The third derivative evaluated at 0 is negative 1. The fourth derivative is 0. The fifth derivative is 1. The sixth derivative is 0. The seventh derivative, evaluating those at 0, is negative 1. Okay, so now it says to find the MacLaurin series for 1, 2, 3, 4, or 1, sorry, just the odds, 1, 3, 5, 7. So P1, if we look back up here and see how it works, and it says f of 0, and that's just 0, because if I remember in the beginning, if I plugged in 0, I got 0 as an answer, plus the first derivative evaluated at 0, 1 times x. So that means that our first MacLaurin polynomial is going to be just x. All right. For the third one, we're going to say 0 plus 1 times x plus, and then we have the second derivative evaluated at 0, which happens to be 0, times x squared divided by 2 factorial, plus the third derivative evaluated at 0, which is negative 1, times x to the third divided by 3 factorial. So if you look at this, that means that the third one is going to be x, we ignore the second one because it's just 0, minus x to the third over 3 factorial. I'm sorry, I should have probably zoomed in a long time ago. There we go. All right, so you can see this first one is just 0, the second one is 0, and we know that because 0 happens every other time that we are going to be skipping half of our terms here. Okay, so there's our third one. So that means that our fifth one, let me go up here, I'm going to say my fifth one, we'd have the 0 to start with again, and then we would have had the first derivative times x, and so that's 1 times x, which is just x. And then we know the second one is going to disappear. We know the third one had a negative in front of it, so negative x to the third over 3 factorial. And then if you look at your fifth derivative, you can see your fifth derivative evaluated at 0 is positive 1. So that would be 1 times x to the fifth, which is just x to the fifth, divided by 5 factorial. And then if we were to do this for the seventh, then it's going to start off the same way. And then the sixth derivative, if you look at it, is 0, so that term wouldn't be there. And then the seventh derivative was negative. Oops, so we're going to put minus x to the seventh over 7 factorial. Ta-da. Okay. So now, here's where the cool part comes in. We're going to go ahead and plug this in on our calculator. So I'm going to say I've got 0.2 minus 0.2 to the third divided by 3 factorial. And if you guys remember how to get to the factorial, you go to the right over to probability, and then it's option number 4, plus 0.2 to the fifth over 5 factorial minus 0.2 to the seventh over 7 factorial. Okay, I think I plugged it all in right. Okay, so there's what we get for that approximation. Now if I type in sine 0.2, you can see that this is accurate to however many, is that 10 decimal places. That estimation was accurate to 10 decimal places, if not more. So that's a pretty darn good approximation there that we just got using this formula. All right, on to example 3. So it's now asking us to specifically use a degree of 6, and we're doing it for cos x this time. And if it says it's a MacLaurin polynomial, then that means you're evaluating it when x is 0. That's what that means. So first I'm going to say that cos evaluated at 0 is 1. I know that because, again, of that unit circle. Looking at when you have 0 for your radians, then your x-coordinate right there is 1. And now I can go ahead and I'm going to find my 6 derivatives. So the first derivative is negative sine. Second derivative is negative cosine. Third derivative is sine. Fourth derivative is cosine. Fifth derivative, negative sine. Sixth derivative, negative cosine. All right, so if we write out the MacLaurin series, we've already done all these evaluations, so I'm going to go ahead and just write them out real quick. We know that anything with sine is going to be a 0, and then cosines were 1s there, so negative cos would be negative 1, positive 1, negative 1. Okay, so for the sixth, for the MacLaurin series, that would be, we start with this one, 1, plus the first derivative evaluated at 0 times x divided by 1 factorial. I guess you don't really have to put the 1 factorial, I'm just following the pattern. Plus negative 1x squared divided by 2 factorial, plus 0x to the third divided by 3 factorial, plus 1x to the fourth divided by 4 factorial, okay, so there is our 6th degree MacLaurin series right there. And so what we really have here is we really have 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Alright, so I went ahead and plugged it in already, and I'm going to say, if I plug in 0.1, because they wanted me to approximate cos of 0.1, then that is 0.995004165 That's what I have, right? And if I just plug in cos 0.1, you can see that at least to 10 decimal places it's the same, which is cool. So I'm going to say that's the same. And then it says that we want to see the error for our approximation. So I'm going to say cos of 0.1 minus, and I'm going to minus off what it was that we plugged in to get our approximation.